So this is the solutions to the ray diagram worksheet. Some of you, we went over this a long time ago. Others, depending on the cohort, not so much. At any rate, the key here is to draw rays. So it said the object was 3.5 centimeters from the spherical mirror, and it had a 5 centimeter radius. So the radius is the center of curvature. That means the focal point is half that distance. So 5 centimeters here, 2.5 centimeters here. Got a compass out and drew that. You can tell, not that great. So the object is here. One ray goes in straight or parallel to the optical axis, the other, and it comes back through the focal point. A second ray you can draw is coming through the focal point, and it reflects back parallel to the optical axis. Those two rays cross right here, so that's where my image location is. So when I do the math for that with the algebraically rearranged version of the lens and mirror equation, I get that this occurs at 8.75 centimeters. The fact this is a positive number for image distance indicates it's a real image, and for a concave mirror, that means the image is on the same side of the mirror as the object. Again, in this case, both on the left-hand side. For the second one, the ray diagram here, if I have an object 1.5 centimeters in height, 6 centimeters from a spherical mirror having a 6 centimeter radius. So 6 centimeter radius means 3 centimeter focal length. Here's the mirror. That's the center of curvature at 6, focal length at 3. Again, first ray coming in parallel to the optical axis, going back and reflecting through the focal point. Second ray coming in through the focal point and reflecting back parallel to the optical axis. You could also draw a third ray there's a couple ways you could do that. If it comes in here like this, it would reflect back at the exact same angle and go down here. Yep, I think that would be a way that you could do that. At any rate, again, using the lens mirror equation, I find my image distance should be at 6 centimeters, which means, that's fantastic, that image should be the same distance away as the object. Obviously, my ray diagram wasn't perfect with that. It's asking you to find the height of the image, so the ratio of image distance to object distance is equal to the ratio of image height to object height, which lets us know our magnification. And that's 1, so the image height would also be the same size, so it's 1.5 centimeters tall. For number 3, here an object is 2.5 centimeters in front of a concave mirror with a focal length of 4 centimeters. That means the center of curvature is 8 centimeters away. So the object is 1 centimeter high. Locate the image with a ray diagram and a lens mirror equation. So here's the mirror, here's my optical axis, there's my object. So just as always, we'll draw one ray as if it's coming from straight in or parallel to the optical axis. It reflects back through the focal point. The second ray that I would draw here is as if it is coming from the focal point, since this is inside the focal point, and that ray coming from the focal point passes over the top of the object and reflects back parallel to the optical axis. That's similar with how our second ray has gone up here. It's just that when the object is outside the focal point, it goes from object through focal point to mirror. Here it goes focal point to object to mirror. We see the same pattern. The other ray you could have done here is one as if it's coming from the center of curvature, because something coming from the center of curvature will always reflect back completely straight, meaning that it hits it perpendicular to the surface. If you notice, I drew that really well. That virtual ray would act as if it's going to that same spot. So the ray of light would go here, hit the mirror, and reflect straight back through the center of curvature again. Any of the two of those 3 rays would help you predict the image location. Here, to find the location of the image with the equation, we use the algebraically rearranged version of the lens mirror equation again, 2.5 times 4 over 2.5 minus 4, I get 10 over negative 1.5. My image distance is negative 6.67 centimeters. That tells me that's a virtual image if my image distance is negative. So in this case, the magnification would be a ratio of image height to object height. That's about 2.67 times as big. And so since this was a 1 centimeter object, it's 2.67 centimeters tall. This one, I had to ratio it down 2 to 1, so that's a little bit annoying. But again, if you have a ray or a mirror like this, which is a convex mirror, if you have an object here to the left, a ray going in parallel to the optical axis would reflect back and up straight, like so. Or pardon me, would reflect back as if it came from the focal point. A ray, as if it's going to the focal point, would reflect back straight, like this one here. So those reflected rays don't ever really cross, just like how these two reflected rays don't really cross. So therefore we have to have a virtual image, and that is small. It is in between the focal point and the mirror surface. So for convex mirrors, you'll always get a smaller or reduced image upright in between the focal length and the mirror. And then if we want to do the height of the image, so if the object was 35 centimeters tall, we look at a ratio of this image distance to object distance. Got the calculated image distance here is actually going to be negative 2 centimeters would be my image distance. I need to make sure I put that down. I think I may have just written over that somewhere. And the reason for that is that, again, that's a virtual image. So hopefully that helps. Change this color to something like this. Okay. And again, calculate the size. It's just a ratio, image height to object, or image distance to object distance, image height to object height. So it is reduced.